previously we talked about a higher level version of how a DFA computes stuff. So we had this idea that you have input brought in as a string, and the DFA reads the symbols from left to right. And upon reading each one of the symbols, it transitions from one state potentially to another state. And upon reading the entire string, it accepts or rejects depending on if the DFA is in a final or accepting state or not. If it isn't, then it rejects. So that's great, but I would like to be able to give a formal definition for computing that we can actually work with beyond just saying, oh yeah, this is how the machine works in a high level. We need a proper way of saying that this is exactly what it does. So what we talked about actually has a formal definition. We're going to define a formal definition of computation or computing for DFAs. So we described them previously, right? So just to give you a recap. So informally, a DFA M defines a language, right? Defines a language, L of M. And also how we process strings with a DFA, right? Now, we can define both of these notions in a very exact way now. So the key phrase is more formally. We want to do this in a very exact way. We want to do it exactly. So that when you pick up this DFA, it doesn't matter if you understand what I mean by transition from one state to another. There's a formal way you could describe this, and it doesn't matter who it is. This is exactly what it does. There is no room for ambiguity. So to do this, we extend from symbols. So you know how we had a transition function that read symbols on a given state, it would transition to another state, right? Potentially. It could either way transition to some state. So we're going to define a transition function, an extended transition function, that will extend from symbols to strings. From symbols to strings. The transition function, right? That's what we're extending. This is the extended transition function. So here's how I'm going to define it for you. So I'm going to define it inductively or recursively, depending on how you want to go about it. I also must stress that you can define this extended transition function in a somewhat different way. So this isn't just one way of doing it. There's also another way of defining it, and you can also derive from that this one, and vice versa. So we're going to use this one because it makes it a little easier to talk about proving the correctness of DFAs. But also, it's easy enough. It's basically the choice of, do you want to read the symbols from left to right or from right to left, inductively or recursively? So I'm going to call it delta hat. And delta hat is going to take in a state and a string. It takes a state a string, and it outputs a state. Which is defined inductively, as follows. So let me define this for you. So since I'm defining it using induction, you can imagine I have the smallest possible string I can feed the machine, which is what kind of string? What string is the shortest one? There's only one of them. There's only one of them. And it's over any alphabet. The empty string. The empty string. So I'm going to start off with the empty string. I need to define what the extended transition function is for the empty string. And from there, I can talk about what and how you would compute a string of any length beyond that, okay? So that's what I mean by using induction. So the basis, so I'm going to use, traditionally I'm going to use the phrase basis just because I'm defining it for you. But this is going to give us a nice inductive structure we can work with if you ever want to prove the correctness of a DFA, for example. But you'll find that extended transition functions are quite common when defining abstract machines such as automata. So here's how I'm going to define the basis of the extended transition function. Suppose I'm in some state, I read the empty string. What did we say in our previous lessons? We talked actually about this idea of a DFA that is given the empty string. Does it transition anywhere? No, it just it stays put right where it is, right? So if I'm in state Q, I read epsilon, the empty string, I just stay put, right? So no symbol has been read. So the DFA stays in state Q, right? Very natural. Now, suppose I give you a string that is of length 1 or more. So that's another way of looking at what we're talking about here. So if a string W equals XA, where A is a symbol, or I'll say where A is the last symbol in W. So it's just the string W. So all I'm doing is I'm plucking off the last symbol. So X is just everything but the last symbol, okay? So its last symbol in W, and X is W less the last symbol. Then, so notice that the way I've defined this for you is that I require a symbol now. So notice that if I wanted to use what I have above and say I have one symbol, what I'm saying is you would have, okay, well, the previous string would be, do you think of it like epsilon, and then A would be the next symbol. So if I had a string of length 1, then it would be epsilon, that symbol. Then, here's how we define it. So I'll have delta hat QW. So what it'll be is first, you imagine you have the transition for Q and X. Then, since I'm going to now read A, so this is how you could think about it. It's just that I've processed X, and now I want to transition upon reading symbol A. So that's what you would imagine, right? You take a transition on this state, because remember, this is a state as we've defined it, right? And then I read on A, it's going to bring me to another state, right? And that's exactly what this would be, right? So after I apply this transition function, I end up with a state. So this is why I'm saying that you could define it inductively or recursively, because to do this relies on me knowing the answer to this. So let's do an example, so that way you can see how exactly this definition works. So it'd probably be a good idea I do an example with you, showing you how this carries out. So I thought I would take a DFA that we talked about last time. Namely, we designed a DFA that reads at least 3 ones. I would like to make it so that it has to read exactly 3 ones somewhere in the string. It doesn't have to be that they're right beside each other, it's just that they have to appear at least, there has to be exactly 3 ones this time. So last time, the way we did that is we created a path of length 3. So each of these had 1. Because most certainly if I had 3 ones in the string, this will get me to Q3. However, I need to make sure that I'm allowing zeros in between this process. Because otherwise, one, I haven't defined what the transition function is in its totality. But also, I need to make sure I define it as given. Because then it's not correct. Because I haven't defined what transitions you do on zeros. Now, when I wanted at least 3 ones, I would have had it so that the final state would be Q3, and I would allow zeros and ones to continue being read, right? However, I want there to be exactly 3 ones. So what's going to happen is I would like to make sure that there's no string that gets accepted that has 4 or more ones in it, right? So I'm just going to extend this idea. So remember, when I've read 3 ones, it doesn't matter if I read more zeros, right? However, if I encounter another 1, then I most certainly have 4 or more ones, right? And here I might read more zeros and ones, but I have a question for you. Which state should be the accepting or final state then? So previously we used Q3 when we had it where we read 3 or more, right? However, we want it to be exactly 3. It definitely wouldn't be Q4, right? Because the purpose that we've just designated Q4 is that it is when the string has 4 or more ones in it. So notice that you have exactly 3 when you're in Q3, right? So this would be the final state. And notice you cannot accept in this state Q4. Some people would call this a trap state, or dead state. Why? Because you're trapping any string that is not desirable, does not have the form, it goes to this trap state. You're trapping all the strings over there. They're saying, hey, look, you're never going to accept because you don't have the correct input. So you'll find that very often these trap or dead states will have it where whenever you're formatting your input, so you want to have it so it accepts a string of a particular form, it'll have it where whenever you have something that is not desirable, it always goes to that one specific state. Here it's much simpler though. So somebody might use the phrase trap state here as opposed to dead state, but I've usually seen them as synonyms. It's just a rather simple case for here. Sometimes when you have more complex looking DFAs, you may have it where you have a trap or dead state. I'll use them just usually interchangeably. You may have one like here where transitions a whole bunch of ones just would never fit the form of the string over to this one state. And its job is just to accept any junk. But it doesn't actually accept the string. It just, any time it transitions to the state, it never escapes it. It's a trap. It's a trap, guys. Okay? so just like over there. So now I think it's important that we actually try using our definition. We'll use it on this DFA. So let's consider W is equal to 1, 1, 1, 1. Then, so first, if I have 4 1s, what should you expect to occur? What should occur? What should occur, everybody? If I read 4 or more strings, sorry, 4 or more 1s in my string, it should be in Q4 when it's finished, right? That's the intuition we have about this DFA. Let's see, and let's confirm that using the definition, or using our extended transition function. So first, and this is how very often you can use the extended transition function, is you imagine you start in Q0 and you're reading the input. So whatever state you put into the extended transition function as the first parameter, that's the state you're currently in. So you can imagine, usually when you're executing the DFA, you would start this at the start state. However, you can totally change what state is there, but that would just be if the DFA was at that state and then it read this input, this string. So it has its benefits in that regard. So for example, if I had it where Q was, say, Q1, I can pass it along a string and it can process from that state too. So this is sometimes helpful when you're proving claims about your DFA or just a DFA. But for us, I just want to execute what it would do with the string starting at the start state. So we start with our basis. The basis says, okay, well, Q0, okay, I stay in Q0. So to read 111, I need to carry out what every time I append another symbol. So I know the answer to that. But now I want to know the answer to Q01, right? It's like I read the first symbol. So how do I get the answer to this? Well, I use the induction part of the definition. So this is saying it's delta hat Q0 epsilon, and I transition on 1, whatever the result is. But what is this? This is just Q0, right? That's just Q0. So I transition from Q0 on a 1, Q0 on a 1, I go to Q1, right? Exactly how you would expect, because I read a 1. Now I have the answer to that. Now I'm presently going to be in Q1. Now if I wanted to just compute directly from Q1, I know how to do that, but I'm trying to show you the definition. So now, suppose I want to do the extended transition function from Q0 on 1, 1. So now I'm reading the second 1. Well, this is delta of delta hat of Q0, 1. Upon reading everything else so far on a 1, well, we know the answer to this is Q1, right? So that means that I'm in Q1 and I read a 1, I go to Q2, right? And then next, delta hat Q0, 1, 1, 1. Now I'm reading the third symbol. Well, this is delta hat Q0, 1, 1, which we already know the answer to this is Q2, right? We just computed that. Upon reading a 1, when I read the 1, I go to Q3. And of course, I read the next 1 to the next symbol. So this is string W. So whatever occurs where the extended transition function here tells us whether the machine accepts or rejects. So delta hat Q0, 1, 1, 1. We already know the answer to this is Q3. I read a 1, and it tells me to go to Q4, right? So the transition function would tell me to go to Q4. But here's the thing. Q4 is not in the set F, the set of accepting or final states. So this means I'm going to reject. So in that case, I reject it. Seems pretty nice, right? So notice that I'm building up my string. when I use this definition like this. But remember still, I know the answer every single time I do this. Every time I read one symbol, I get the answer. And that's whatever goes right in here. Right in there. Right in there. So let's do another example. Let's do another example. So let's consider the input W is 1011. Then let's go through the process here of using the extended transition function. So delta hat of Q0 epsilon, well, it stays in the same spot, right? it's Q0. Delta hat upon reading the first symbol, well, this is just delta of delta hat, Q0 on the empty string. When I read a 1, right? But we already know this answer, this is Q0. And this is, I read a 1, right? So in this case, I go to Q1. Then next, let's go delta hat Q0, and I read the next symbol, which is a 0. So this is going to be delta, so I apply the inductive part of the definition. So I have delta hat Q0 upon reading, oh sorry, I need 10. It needs to be 10 there, because that's the string I'm reading. So I have Q0 on 1, right? The previous symbol, upon reading a 0. So notice this is what I've currently read so far. This is what I'm going to be reading next, the 0. Now the answer to the delta hat of Q01, that's just Q1, right? Then I read the 0, so Q1, when I'm in 0, when I read a 0, I stay in Q1, correct? I stay in Q1. Then next, I read a 1, right? That's the next symbol. Delta hat of Q0, 101. Well, this is just delta, so I use the inductive part of the definition. So delta of delta hat, Q0, 10. When I read a 1, so that's just this part all goes in here. The next symbol is what I'm transitioning to, right? Now the answer to this is Q1. So upon reading a 1, I go where? Where do I go? Where am I going? Do I stay in Q1? No, there's a transition from Q1 to Q2, right? So now in Q2, and then I read the last symbol, so that's what the DFA will do next. So delta hat Q0, 1011. I do delta hat Q0, 101, right? Those are all these symbols before I read the next one. Then I transition on a 1, the one I'm currently reading. So we already know the answer to this is Q2. So the transition on Q2, when I read a 1, it says to go to Q3. That's what the transition function tells me, based on the transition diagram I have over there. Well, question. Does the DFA accept on W, or does it reject it? Accept or reject? Accept, reject. Which one is it? Well, let's take a look at our states over here. We have Q0. This isn't an accepting state. This isn't an accepting state. So Q1 isn't. Q2 isn't. Q3 is. Q4 isn't. Q3 is an accepting or final state. So that means that Q3 is the current state we're in, and Q3 is a final state, right? So that means that W gets accepted by the DFA. So this is how we could define the extended transition function. That brings me to one last point, as I promised. Let's head over here. No, don't get back here. Get back here. Get back here. We're heading over here. let's head back over here. So I promised I was going to show you two things. First, how the DFA actually gets computed. And the extended transition function provides such a thing. But also how we define the language of a DFA. Now that we have the extended transition function. So now we have a way to describe strings accepted or rejected by a DFA, right? So now I can define formally for you the language of a DFA. So you know we had L of M for a DFA M. Now I can define that formally for you using the extended transition function. So the language of a DFA, so for a DFA I could define its language now. So the language of a DFA, which we'll denote, we'll call it DFA M, is denoted by L of M. Is as follows. So it's actually this, it's a language, right? Is as follows. L of M is equal to all strings W such that what? We can actually define this using the extended transition function. I'll give you a bit of a tip. Do you notice that whenever I accept, that state is in the final or accepting states? So whatever comes out as an outcome, whatever the state is has to belong to the final or accepting states of the DFA. So what goes right here? Well, I already gave you the heads up that it's going to involve the extended transition function, right? And the extended transition function takes two parameters. What should those two parameters be, everybody? What should they be? Well, as I alluded to earlier, we start at Q0, right? That's where the DFA begins execution. As remember, like I told you, you can use this extended transition function at any one of the states. It'll tell you what the DFA will, what state it will be in upon reading that string, for whatever state you wanted to start at. So in this case, we start at the start state, as you'd expect, and it reads W, right? So this is how you can specify the language of a DFA. So the extended transition function, remember, this tells you a state. So starting in Q0, it reads string W, and upon reading string W, if the state, which is the result of the extended transition function, this is what it outputs, if it belongs to the set of final states, then the DFA accepts, and all strings that are accepted by the DFA dictate or describe a language. And that is what L of M is.